Now in this example 3, I am going to illustrate how to solve a definite integration problem involving integration by parts. Alright, involving integration by parts is definitely going to be different from substitution problems. Alright, so let us get it started straight away. Now, integration by parts involving limits. First, you do Hesper-normal. We need to decide who to keep. So according to LIATE, we know that algebra comes before the exponential, so we will keep the algebra x. We integrate e to the power 2x, which we get half e to the power 2x, minus you integrate, you differentiate the one you kept, which is 1, and you copy down the integrated expression dx. Okay, so this is what we have learned in the previous chapter, integration by parts. Now, because this is an integration by parts involving limits, so how do you put in the limits? Take note that over here, you have already performed the integration. Because you have already performed the integration, we need to put in the limits from 0 to 1. Okay, since you have performed the integration, you have to put in the limits from 0 to 1. Then, since this is an integration problem involving limits, and here is still an integral, you need to put in the limits 0 to 1 as well. Okay, clear? So this is how you illustrate, how you make use of integration by parts and do it with limits. Then, what do we do to this part? Same thing, substitute the top limit minus substitute the bottom limit. So you substitute the top limit inside, you're going to get half e to the power 1 minus substitute the bottom limit, you're going to get 0. Okay, sorry, when you substitute the top limit, you're going to get half e to the power 2. Okay, minus bottom limit, you get 0. So now we're left with this 0 to 1. You can write the constant half outside the integral. Okay, so what do we do next? Likewise, compute this integral Hesper-normal. Because it's a definite integral problem, you put square bracket. So this is going to give you half e to the power 2x from 0 to 1. Now take note that in definite integrals, we don't put plus c. No more plus c. Because we are integrating a definite integral, meaning we are going to substitute limits. So the c has been evaluated. Half e squared minus 1/4 here. So you substitute the top limit, you're going to get e power 2 minus you substitute the bottom limit, you're going to get e power 0, which is 1. So what follows? You get half e squared minus 1/4 e squared plus 1/4. And final answer, 1/4 e squared plus 1/4. Alright, clear? So this is how you do integration by parts involving limits. Okay? I shall illustrate a second example. How do we evaluate definite integrals when it involves integration by parts? Okay? So let me repeat again. If we ever need to integrate by parts and it involves limits, all we need to do is really to do out the integration by parts as per normal, but whichever parts that have been integrated, you need to put in the limits. And likewise, any integral should also have the lower and upper limits. So what do I mean by that? First, we realize that we need to do this integration by parts by treating as though there's a 1 in front, where 1 belongs to algebra category. So we need to decide 1 to keep. We'll keep tangent inverse 1 over x, and we integrate 1. Integrate 1, you get x. Minus, you integrate what you have, differentiate the one that you have kept. So we need to differentiate tangent inverse 1 over x, which gives us, not forgetting to differentiate chain rule, use this expression 1 over x, which gives us negative 1 over x squared. And then we copy down the thing that we have integrated. Okay, because this is a question involving limits, so whichever part you have finished integrating, you put in the limits. And this integral, you also need to put in the limits. Okay? So simplifying, you're going to get square root 3 tangent inverse 1 over square root 3, put it in the top limit, minus, put it in the lower limit, tangent inverse 1 over 1, which is 1. So this is the first part of the answer. Minus, now we need to simplify this expression a little bit, from 1 to square root 3. This is what you obtain. Now, back to this. We know that tangent inverse 1 over square root 3 will give us a special angle, 30 degrees, which is pi over 6. So square root 3, pi over 6. Tangent inverse 1 will give us also a special angle, 45 degrees, which is pi over 4. Alright, minus. Negative here, become a plus. So simplify a little bit, we're gonna get x over x squared plus 1 dx. Now, further, we need to integrate this expression here. We realize that this expression is a rational function, where the numerator is a polynomial in x is of 1 degree less than the polynomial in the denominator. So what do? We can think of the f prime over f formula. So differentiating the denominator, you're going to get 2x. So I need a 2x in the numerator. So you put in a 2, but you need to compensate it by putting in a half outside. So what follows? Now we are ready to integrate. Integrate this expression simply ln bracket x squared plus 1. Need not put a modulus because x squared plus 1 is always positive, no matter what values of x you put in. Not forgetting my limits, 1 to square root 3. Substitute the top limit, you're going to get ln 4 minus, substitute the bottom limit, you're going to get ln 2. Now, you can still further simplify ln 4 minus ln 2 using laws of logarithm. Will give us ln 4 divided by 2, which is ln 2. Okay, so you can leave your answer in this final form. Alright, so this is how you deal with limits for integration problems involving integration by parts. Okay, and I leave my answer in the exact form as requested by the question. Okay, we can also use a GC to help us double check whether our answer is correct. So let us do a quick check. Of course, you remember it's from this function. All we need to do is really just to put in the limits accordingly. 1 being the lower limit, square root 3 being the upper limit. Okay, not forgetting the integrand, meaning the expression to be integrated, and this one is tangent inverse 1 over x. Last but not least, do remember to put in the variable that you're integrating with respect to, which is x here. So just press enter and the calculator will give you a numerical answer. So let us double check whether our answer is correct or not. What we have is pi times square root 3 divided by 6 minus pi over 4 plus 0.5 ln 2. Alright, you get the same answer. So it verifies that your integration is correct. Okay?